Science is one of the most important subjects we teach next to reading and writing. The more we know about science, the better off as a civilization we're going to be. Our national security depends on science and producing students who are understanding of science, mathematics, and engineering concepts. The next generation is going to have to solve the problems that we have created in the world, and they'll need a strong science background to be able to do that.
Hello, I'm Kimberly Singletary. According to the Bureau of Labor Statistics, employment of life, physical, and social science occupations is projected to grow 10% from 2016 to 2026, resulting in about 124,800 new jobs. On this episode of Carolina Classrooms, we'll explore ways for educators and parents to get students excited about science and to prepare them for these future careers. Bill Austin, assistant principal at Oakland Primary School in Sumter, dropped by our studio to show us some shocking experiments with static electricity.
Hello, I'm Bill Austin. I'm an assistant principal right now at Oakland Primary, but I've been teaching science for almost 24 years. I'm passionate about science, and today I'm going to spend a little bit of time with you doing a little bit of science to help you understand a little bit about our great push for STEM and STEAM education here in South Carolina, and particularly in my district. I have a little helper with me today, my granddaughter, who's actually been through my robotics class. She's a 4th grade student at High Hills Elementary School in Sumter, and we're going to use her today as a model and a demonstration. Say hi, Maddie. So away we go. Today we're going to talk a little bit about a 3rd grade standard on electricity. Now let me start by saying that electricity is dangerous and you need to be careful and be supervised anytime working with electricity. We're going to be working with static electricity today, which creates lightning, which is a very powerful force. The forces we're going to be using today won't be as bad, but they're still dangerous if not supervised and properly executed. So be very careful when using electricity. Now today we're going to talk about static electricity, and we start teaching electricity in school at 3rd grade with our state science standards. And we're going to talk a little bit about static electricity, and I'm sure you know a little bit about static electricity because we see it in our everyday life. Now I'm going to charge this balloon a little bit. Static electricity is caused when 2 dissimilar objects rub together, causing one to be more charged than another. We're charging this balloon right now, rubbing it on Maddie's hair. And now we're going to pick up some pieces of paper that I brought. That's a static charge, and that's what you'll see as with static electricity. It's kind of like rubbing your feet on a carpet and then touching your sleeping dad in his lounge chair on the back of his neck and watching him jump and scream. Now we're going to do a little bit more with static electricity. We're going to fill Maddie with static electricity. She's standing on an insulator, and we teach insulators in our 3rd grade science classes. And she's standing on one now, which means electricity can't pass through her to the ground. And electricity always wants to go to the ground. Maddie, put your hand on the ball for me, and keep your hand there at all times. And here we go. We're going to start filling Maddie with electricity and see what happens. Shake your head for us, Maddie. Now if you look at Maddie's hair, the longer she's attached to the Van de Graaff generator, the more static fills her body. It has nowhere to go because she's standing on an insulator. Shake your head a bit more. And you can see her hair is filling with electricity, looking for a way to get to the ground. It has no way right now to get to the ground. So it is filling her up and filling her up. Now let's make a prediction, and predictions are what we've talked about in science. What do you think will happen when I turn the Van de Graaff machine off? Let's see, shall we? Keep your hand where it is. Absolutely nothing. Her hair continues to be filled with static electricity with nowhere to go. What do you think will happen if we take her hand off the ball? Maddie, take your hand off the ball and let's see what happens. Oh, the electricity still has nowhere to go. Let's give it a path to the ground. I think I'll be the path to the ground. Watch her hair as she reaches out and touches me on the hand. You'll see that the static electricity found somewhere to go. It went to the ground. And that, boys and girls, is static electricity. It's caused by rubbing 2 dissimilar objects together. On the Van de Graaff generator, this large rubber band rotates in here and pushes against a piece of copper, rubbing together as it goes, creating the static charge, which then filled Maddie with electricity. You can get a good example of this in the atmosphere. When clouds rub together, they build a static charge. And when the clouds rub together enough and the static charge is built, where does that electricity want to go? To the ground. That's what creates lightning. That's why you don't stand under a tree, because as we're going to show you in a minute, the electricity wants to take the shortest path to the ground. And that tree that you might be standing under is going to be the shortest path. So you don't want to be standing under a tree during a lightning storm. You want to get to the lowest point possible and give that lightning an opportunity to strike everything except you. All right, so now we're going to move Maddie. Maddie, will you come over here for us, please? And this is a plasma ball. Plasma is another form of energy. It's not electricity, but it acts just like electricity for the purposes of this demonstration. So let's put your hand on the plasma ball. And you can see that that plasma is looking for a way to the ground, just like electricity. And right now, it's trying to find a way to the ground, and it can't because Maddie, again, is standing on an insulator. Maddie, I want you to grab this bulb. This is a fluorescent bulb. Fluorescent bulb is now lit because the electricity passing through it excites the neon in it, or the argon, and it is lit right now. As I move my hand down, I'm the shortest path to the ground. As I move my hand down, you'll notice the top half of the bulb is not lit and the bottom half is, because it's looking for the shortest path to the ground. This is lit, that's not. Once again, boys and girls, electricity making the shortest trip to the ground, which I happen to be on. If I move my hand up, you'll see once again it's fully lit. Maddie, take your hand off the ball. The light goes out because there's no power going to the bulb. Put your hand back on and you'll see the bulb comes back on. We just turned Maddie into a human switch. Thank you very much, Maddie. We appreciate all you're doing. Boys and girls, that's a quick demonstration of static electricity. We teach static electricity starting in 3rd grade, and we use electricity in a lot of our lessons all the way up through 6th grade and into our early physics classes in high school. I hope this demonstration helped you understand the properties of electricity, and I hope you can use this in what you do. Thank you very much.
The State Museum offers many educational programs that teach kids about science. Many follow the state standards for teaching science in the classroom.
Hey guys, my name's Laura Ibarra-Kane and I'm the Education Manager here at the South Carolina State Museum.
And I'm Diana Yoder. I'm the Science Education Manager here at the South Carolina State Museum.
We're here doing some pretty cool stuff with you today, including chemical reactions, and these are really cool salt fires where Ms. Diana's going to show us some really cool things that happen with ionic and covalent bonds and energy transfer. So what do we have here?
All right, so we're going to be looking at some properties of the different compounds, like Ms. Laura said. We have a few different salts on our table. The first speaker is our calcium chloride. Next, we have our cupric sulfate. Next, we have our strontium chloride. Next, we have our potassium chloride. And finally, we have our cupric chloride. Now, each of these salts are made up of 2 different elements. Elements, of course, are made up of atoms. We've got our protons and neutrons hanging out in the nucleus, while we've got the electrons orbiting around the nucleus. Now, depending on which element you have, you're going to have a different number of electrons. So the number of electrons also means you're going to have different amounts of energy. So what we're going to do is we're going to add a little bit more energy to our compounds and make those electrons excite. They're going to jump up to a new energy level, but they don't want to stay that way forever. They're eventually going to fall back down to their ground state. And when that happens, the energy they had absorbed has to go somewhere, so they're going to release light. And depending on how much energy that was, we'll get a different color light. So let's go ahead and get started. For safety reasons, we're going to be setting things on fire, so I do have my fire retardant gloves here.
And I'm not using any because I'm not lighting the table on fire.
Yeah, Miss Laura's not using the lighter. I also have glasses on to protect myself from any splashes or anything like that.
But I will be putting my goggles on.
Excellent. So first, before we light any of our salts on fire, I'm going to take some of my methanol and I'm going to show you what color this burns by itself, because just like those other compounds, it has a specific amount of energy and is going to be a specific color as well.
Cool.
So I have a special table. Normally you would not do this on the table. Oop. We just have a little extra. I'm going to put a line on our table, and we're going to set this on fire. So, scooch, set my lighter on.
Ooh.
Now, got a little extra. You can see the color was blue. There's a little bit of orange in there, but for the most part, our methanol burns blue.
So every time it goes into one of these, we're going to see blue first, and then we'll see the actual color after.
Yep. We'll see that methanol catch on fire first with that blue color, and then we'll see what color the salt really is.
Okay.
So let's get a little bit more. And we're going to start with that calcium chloride. Let's get a little more.
This salt right now looks white, but we have a couple different colors on the table. One of them is blue and one of them is green. Very cool.
Okay. So now that our methanol's in there, I'm going to grab that lighter.
Got it, right?
So
Yeah.
there we go.
Ooh, that one's kind of orange.
Yeah.
Yeah. Ooh. Awesome. So that one's kind of an orange color when it burns.
Yep, we've got a little bit of the blue in the background, and it's also orange. I'm just going to take some water, and so just pour a little bit of that into our salts to get that to stop burning. Next, we have our cupric sulfate.
And this is the blue one.
This is the blue one.
Now, just because a salt is a color, does that mean that it's necessarily the color that it's going to burn?
We can find out in a second. Let's add some of our methanol.
Ooh.
Now, I don't think it looks too blue. I think it looks green.
Yeah, that's a beautiful green color. Yeah. Very cool.
Awesome. So again, I'm just going to pour a little water, set that fire back down. And next we have our strontium chloride right here.
That's another white one, but the salt is a lot finer. It's
Yes,
really
it's a
tiny on
little
this one.
smaller grain.
And you keep capping it because the methanol
So it
evaporates quickly.
evaporates quickly, so if we left this on, we wouldn't have very much left over.
Ooh,
Oh, there we go.
that's a beautiful red.
Yep. Didn't even see any blue there. It went straight to
Yeah.
red.
That was great.
Yeah. All right, let's get a little water in there. Set that fire down. Next is our potassium chloride. This one I think is even finer grain.
Yeah, that's really tiny.
So we've got some blue. I'm gonna give it a second.
Is that one yellow?
There's a little bit of orange coming through in the bottom. This one always likes to be a little bit blue at
I gotcha.
first.
Oh yeah, you
There
can
it
see it
goes.
now.
Yep.
Yeah.
Awesome. Here goes the water. And then the last one, this is my favorite. We're gonna do the cupric chloride.
And the salt looks green.
Mm-hmm.
So,
So it's burning blue for a second, but then we get those beautiful teal colors coming out.
That's really cool. Oh yeah, you can see, and it's sparkling a little bit. Awesome.
Awesome, so we're gonna set that fire out. And so we just excited,
There we go.
we excited a bunch of electrons and they cooled back down, and that's why we got our different colors.
Awesome.
Project SEED, a program of the American Chemical Society, has been offered at the University of South Carolina since 2010. The program gives economically disadvantaged high school juniors and seniors an opportunity to work with a mentor in a science lab for 8 to 10 weeks. At the end of each session, the students present and explain their research on posters.
Benzene microcycles are formed from C-shaped spacers and two urea groups. In this diagram, you see the C-shaped spacers and the two urea groups attached.
So usually we start the program at the beginning of June and finish at early August. The poster is a showcase how students work in the summer to summarize their research work and to show how they present their research data and funding to the public.
It's been 2 years I've done this, 2 summers. It's been an 8-week program where you work alongside a mentor who's a graduate student. You get to learn a lot about a special field of chemistry, or yeah, it's all chemistry, but it's different fields from fuels to polymers and anything in between.
I think it's valuable for students because they get exposed to research in a laboratory setting, which is a very rare opportunity for a student in high school. So they get to see how an active, functioning research lab works. That being said, they learn that some experiments work really well and sometimes things don't work really well, and how to troubleshoot that, which is exactly what we do every day.
This is my second year and I enjoyed both years. Like having hands-on and being able to work with college students and graduate students and asking questions and learning about chemistry was fun. It actually opened my eyes because before I planned to do biology, but coming in and actually having hands-on and working with chemicals and seeing how it actually is, it made me switch my decision to chemistry.
I like to tell students to ask questions, and I think that's the best way to get engaged in science and start thinking about what are you interested in? Is there a particular phenomenon? Is there something about science about our world that you want to know how it works? And usually with that, you delve deeper and deeper, and you find out what is known, what isn't known, and how I can contribute. So that's a really good entry point for science.
I definitely tell them to shadow somebody. I mean, even if you have no idea what area of science you want to go into, kind of learn about it, see if there's somebody you can shadow or talk to. I mean, when I was an undergrad, I switched between 3 science majors before I figured out that I liked the chemistry lab because staring at a plant wasn't really what I wanted to do. So just kind of don't take anything off the table, kind of see what is it that you like the best, because not everybody likes chemicals. Some people like, animals and things like that.
Often used to communicating with colleagues, communicating with people that specialize in exactly what we do. And so working with high school students challenges us to communicate more effectively at a different level and to distill our thoughts much more simply than we would normally.
Probably start from my perception, as a professor. So we are here not only for research and teaching, but also for the community. So we want to make our students better, family better, and community better. For students from family economic disadvantages, sometimes they are in a position not fairly compete, into future careers. For example, entrance to college. So if we can spend 8 weeks in the laboratory setting and know how the science looks like, so this will be better for their future careers. I'm very proud that, in 9 years, all students from my program went to college, 100%. So this record I'm very proud of, I want to keep that.
The students are paid for their time working in the lab. Faculty members choose students whose posters do the best job of presenting their work and award them each an additional $300. For more information on Project SEED and how to apply to be a part of the program, visit sc.edu/Project SEED.
You ever see a bug walk across the top of the water? Well, that's possible because of a force of nature called surface tension, how tight a particular material is. I'm going to take this skewer, and I'm going to take what I know about surface tension, and I'm going to insert this skewer right through this balloon. Shall we see if it works? Oh, maybe I didn't use what I know about surface tension. Let's try that again and see if I can't make this work. Knowing what I know about surface tension, I'm looking for the thickest part of the balloon, which happens to be at the very crown and the very bottom. As you'll see now, I've inserted this skewer through the balloon without popping it. A demonstration of how science can help you not pop balloons.
Hey guys, my name is Laura Ibarra-Kane, and I'm the Education Manager here at the South Carolina State Museum.
I'm Matthew Dantzler, and I'm also an educator here at the South Carolina State Museum.
And we're going to be doing some pretty cool chemical reaction experiments with you today. So I'm going to start with a small one that's easy to do in your classroom or at home, and Matt here is going to do a really cool big one that we like to do here at the museum in some of our programs. So we're going to start down here with our little beaker, and this just has water in it. I've dyed it a little bit for you so you can see a little bit, but it's just water. And then we're going to take an Alka-Seltzer tablet, and when you put an Alka-Seltzer tablet in water, it starts to fizz. And you might have seen those at grandma's house or something when somebody had an upset tummy or they were sick. So they put it in water and it starts to fizz, and it's supposed to make you feel a little bit better. So if I take this away though, we're going to put it in here. Now this is a film canister, and these, back in the day, we had cameras that had film roll in them, and they don't make those very much anymore, so you can go to a lot of different film stores and get these for free if you want, so you can do this experiment at home or in your classroom pretty readily. I've already filled it about halfway with water, and I'm going to take my Alka-Seltzer and put it in there again. And like we saw before, when we put Alka-Seltzer in water, it starts to react and we get gas from it. But this time I'm going to put the lid on top, and when I put the lid on top, the gas isn't going to have anywhere to go, so it'll start to create pressure, and as it creates pressure inside, eventually the lid will explode. So that's our little simple one that you can do at home or in your classroom. And now Matt is going to do the really big, cool one. So tell us what you're going to do, Matt.
Okay guys, so we're going to do a chemical change on a bigger scale. And for this, we're going to have to use safety precautions. So we have to have gloves, goggles, and for anybody that has long hair, you probably want to have it pulled back for safety measures. So what we're going to be using is 3 different types of solutions. We'll be having dish soap, or hydrogen peroxide, and sodium iodide. So what we're going to do, we're going to take our dish soap first, and we're going to pour just a couple of few drops in there.
Very scientific, a few drops. Okay, I'll take that for you.
All right, thank you. And next we have 250 milliliters of hydrogen peroxide. So at stores, you guys can get hydrogen peroxide for 3% or 6%, but this is 30%. It is extremely strong.
What happens if we get that on our skin while you pour?
So what happens if we get this on our skin starts to itch a little bit, so it causes like a very severe itching. But that's why we have safety gloves on and safety goggles. So we're pouring this guy in. And next what we're going to do, we're going to slowly but carefully swirl our dish soap and our hydrogen peroxide.
So why are you swirling it around?
We want to make sure we get that dish soap and the hydrogen peroxide together so it can make a better and more clear experiment or chemical reaction.
Cool.
So next what we want to do, we want to make sure that everything is off the table. And what we're going to add is our 50 milliliters of sodium iodide.
And when you add that in, what should happen?
What was going to happen? It's a whole lot of science is about to happen, guys. So here we go. Nope.
That's awesome! So that's your bigger chemical reaction that you can do, or that we do here at the museum. So really cool, really fun.
For more information on programs at the State Museum, check out their website, scmuseum.org/education. Thanks for joining us. We'll be back on TV in February. You can find more education stories from around the state on our website, carolinaclassrooms.org. Keep in touch on our Facebook page or by email and let us know what you'd like to see on Carolina Classrooms. Bye-bye.